Now that we've covered force diagrams, first law and second law, it's time to get into systems. All right. A system is when two or more objects are connected and accelerate at the same rate. All right, so we can have two boxes connected by a string going at 5 meters per second squared. It's how you approach that sort of problem. So this is an example of a system with two bodies. We have one mass that's going to slide horizontally across the table, and then a second mass that's going to fall towards the ground. And it's entirely possible to find out what's going on here with a little bit more information. Just for sake of consistency, we'll call the mass on the table mass 1, and the mass on the falling down mass 2. Okay? So, a couple of things we need to ask ourselves about this system is, first off, what will cause these two objects to move? All right? I think it's kind of common sense. If, say, you were holding on to the hanging mass and then let go, then it would start moving. Whereas as long as you're holding on to it, it's not going to move. So it's the falling mass, or mass 2, that causes the objects to move. All right? And the force of that mass that does this is the force of gravity, or Fg2, which is going to be equal to mass 2 times gravity. Okay? So, mass 2, or the falling mass, causes the object to move. Alright? So, weight of the hanging or falling mass. So, another question to ask is, what is going to resist movement? Alright? We're used to resistance being friction. One thing is, typically, we're going to work with these problems assuming that air resistance is negligible. Because typically it is. This isn't going to fall a huge long distance. So what creates the greatest resistance is the friction of the mass on the table, or mass 1. Alright? So we'll call this force of friction 1. And to find force of friction 1, you'll need to use your force of friction equation, except it's going to be the normal force of mass 1. So if you think about mass 1, we've got Fg1, and it's sitting on a table that's horizontal, so that'll be Fn1, and they'll be equal to each other. So really, Fn1 is equal to Fg1, which you can calculate by getting mass 1 times gravity. Okay? So when we need to draw a force diagram for a system, we don't draw the forces separately for the two masses. We combine them into one single diagram. Okay? So there's only one force diagram. In the center of the force diagram, where we write our mass, all masses contribute. Okay? So mass 1 and mass 2 are in the center of the force diagram. So let's draw sample 1 in here. So inside we'll have mass 1 plus mass 2. And then you have to depict the forces that cause the motion. Previously, up until this point, it was always applied force that would cause the motion. But in this case, it's the force of gravity of mass 1. Of mass 2. Now, even though force of gravity points down, this whole system is moving, most of it, or at least the top mass, is moving sideways. Alright, so we're just going to stick with leaving our force that causes motion going to the right, like an applied force, but in this case, it's actually Fg2. Okay? And then you have to depict the forces that impede the motion in the other direction. So we'll have, in this direction, our force of friction 1. Alright? Now, this equation, F net equals ma, still applies. Alright, so if you are able to figure out both Fg2 and force of friction 1, then you can combine those to find your net force and maybe solve for acceleration, something like that. So here's another picture of what's going on, and I left off my acceleration arrow on the last one. But you have Fg2 going to the right, force of friction 1 going to the left, and your acceleration obviously is going to go with what's causing the motion, Fg2. All right? If it's moving, then we know our acceleration is towards the falling mass, because the direction towards the mass on the table, that won't make the movement happen, so it can't accelerate in that direction. Okay? Let's do a quick sample. So we're just going to make up some numbers. Let's say that our mass 1 is 34 kilograms. And let's say that our mass 2 is 62 kilograms. Okay? And let's say we happen to know that our coefficient of friction of the table is 0.27. From this, let's find acceleration. How, you might ask? Well, let me make this a little smaller so we have some room for work. There's our sample problem. We need to set up our system's force diagram. So our force diagram is going to look like this. We will have one force going this way, one force going this way, and we know our masses are going to be 34 plus 62, or 96 kilograms. Okay. We know the force here has to be Fg2, so let's find Fg2. So that's going to be Fg2 equals m2 times gravity, or it'll be 62 times 9.8, which gives you 607.6 newtons. Okay, so now our other force is going to be force friction 1. Let me draw on my acceleration arrow. Sorry, I do have a tendency to forget those. So force of friction 1, we talked about it, is equal to mu times normal force of 1, which based on a diagram of just that box, we know Fg1 and Fn1 are the same. So really we need to do mu times Fg1. So Fg1 will be 34 times 9.8, or that ends up being 333.2 newtons. So force of friction 1 is equal to that number times 0.27. Alright, which ends up being 89.2. Alright, so let me scoot this up just a little bit. We still need to find acceleration of our force diagram, but now that we have forces on the both sides, we can find F net. F net is equal to Fg2 minus force of friction 1, which would be 607.6 minus 89.2, which is 518.4 newtons. So if we want to find acceleration, F net equals ma, divide by mass to get acceleration. So your acceleration is going to be equal to your 518.4 newtons divided by your total mass, 96 kilograms, and you end up getting 5.39 meters per second squared. So that's just one example problem of how you could work with a system. We will work with some more problems in class, and we'll even work with some other systems as we continue next week. So make sure you do the online form, and I will see you in class.